also into star formation. Okay, so if I plot the star formation rate on the y-axis and the mass of the galaxy in stars in the x-axis, I've got three sequences now. They're inverted. A sequence of the galaxies that are called stars. That is so-called often the main sequence, but it's the star formation sequence of the galaxy. I've got the red sequence, which is passive galaxies. They're not forming stars. And in between, a region that is a valley because it doesn't have that many galaxies, which you would call the green valley. But this is already telling us quite a lot about galaxy evolution, because all galaxies must have formed stars at some point, right? Because galaxies have got stars. That's what the x-axis says. They've got masses in stars of the order of 10 to the 8, 10 to the 9, 10 to the 11 solar masses. So galaxies must have started here on the main sequence, on the star formation sequence, and they must move somehow to the red sequence. There is a mass dependency, as you can see. The low mass galaxies have never, not many have moved to the red sequence, but that evolution from the red, from the star formation sequence to the red sequence of galaxies is one of the things that we try to understand in galaxy formation and evolution. This is connected to the morphology that I mentioned before. Here, the star-forming galaxies tend to be spirals or irregulars. The non-star forming galaxies tend to be more lenticulars and ellipticals. That is not always one-to-one correspondence, but that's good enough for us. And the other thing that is important to remember is that environment affects galaxy evolution, at least affects the properties of galaxies. So where a galaxy is affects what the galaxy looks like, the morphology, and this plot here is the famous morphology density relation that Alan Dressler quantified in 1980, but even Hubble and Thomson in 1931 realized that in high density environments, the vast majority of galaxies are either lenticulars or ellipticals. In low density environments, the vast majority of galaxies are spirals or irregulars. In low density environments, the vast majority of galaxies are forming stars. In high density environments, the vast majority of galaxies are not forming stars, being the morphology. So that's all you need to know about galaxy evolution to understand what I'm going to tell you later. In order to understand galaxies, you need to take pictures to get colors, and you need to take spectra. And I'm going to say that probably the most successful astronomical collaboration ever has been the Sloan Digital Spectroscopy. It's published more papers than anybody else. It's published papers with more citations than anybody else, even the Hubble Space Telescope, and even JWST. And is doing that with a very modest telescope, right? So we don't need all the time 10 or 13 telescopes to do good science. Yes, you need good instruments and good brains. And I joined Sloan in the fourth incarnation, Sloan Digital Spectroscopy 4, that used this telescope at Apache Point Observatory. That's the observatory. And Sloan, the first thing that they did is they imaged the sky. They imaged about a third of the sky in 5 bands using what it was at the time, the largest CCD camera that there was. And there are many hundreds of millions of galaxies there. And there are the pictures that we use sometimes to classify galaxies in morphology. Obviously, in this plot, every lump is tens, hundreds of galaxies. Okay, so this is just to show the whole coverage, which is about a third of the northern sky as the image. But we also need spectra, and Sloan was one of the first places where they used fibers to locate the end of one fiber on a metal plate, plug it by hand with a hole, plug a fiber optics. I learned all about fiber optics from Jaime Zambrano many years ago. You plug the fiber optics there, the light comes through the fiber optic, go to a spectrograph, and then you get a spectrum, which tells you how much light there is in different locations of the galaxy. And you can see here emission lines that tells us things like star formation is going on there, or maybe AGN activity, and that's what it was. So by doing that, Sloan got spectra of well over 1 million galaxies, and this animation is just to show that. Let's just go back, it's going very fast. This animation just shows each one of these pictures is a real picture for Sloan from Sloan, and it's in the right location because we know the redshift. Okay. So Sloan imaged and got spectra through fibers for millions of galaxies. And that helped us to understand quite a lot, because if you put a fiber on a galaxy and get all the light of the galaxy, you can understand, you can measure using not very difficult physics, the star formation rate. You will be able to measure the chemical composition. If you're a bit clever, you can even get the star formation history. You can measure the kinematics, how fast the stars are moving. You can measure whether it's an AGN, whether it's a black hole at the center that is being fed and producing energy, chemical abundance, stellar masses. But you do that for the whole galaxy at the same time. The galaxies we've seen are very pretty, and they do not behave the same in every region. There is two merging galaxies here, and you can see that whatever happens here at the center and whatever happens at the periphery is different. The center is red, and there's maybe AGN activity there, and there is lots of star formation in the periphery. So it's interesting, it's important to get information that is spatially resolved. That is information that gives you the properties of the galaxies in different regions. The properties here and here are different. And so we want to understand how galaxies, the galaxies properties, the star formation, the chemistry, the kinematics happen in different positions. And that is what integral field spectroscopy is. An integral field spectroscopy, what it does, it gets you a spectrum of every location of the galaxy. And then you get a data cube that you can understand it in two different ways. X and Y are always the position of the sky, and Z is always wavelength. You can either understand it at a spectrum at every point of the galaxy. So in every point of the galaxy, I know the spectrum wavelength. Or I can understand it with having many thousands of images with one single color, whichever way. But that data is normally called a data cube, is what I've been using. This is the product of integral field spectroscopy. And that is being developed over several years, even from the 1990s. The first spectrographs like that were developed. Galaralto was one that done lots of interesting work. A survey called Khalifa, which in many ways is a precursor of what the one I'm going to talk about. And if you do that, the amount of information, I just want to overwhelm you here with this picture on what you can extract once you get that information. Okay, yes, you get here on the top the velocity. The right-hand side here is moving away from you, sorry, towards you. The left-hand side is moving toward, away from you. So there is a disk that is moving there. We can see that the center of this galaxy, the stars are moving very fast in random motion, that is velocity dispersion. Then if you're an aficionado of kinematics, H2 and H3 and H4 will mean something to you. Is just how far away from a Gaussian we are in the velocity, but you can also learn about, I don't know, the emission in O3, which is about AGN activity. We can measure H beta and absorption and emission, tells us about the age of the stellar population. This index I'm 15 and other indices tell us about the chemical composition. You can look at the velocity of the gas. This is the velocity of the stars. Ages, metallicity, you get all of that information if you got integral field spectroscopy, and if you got it, and you got it for every location in the galaxy. So MANGA is the survey I'm going to be talking about, and MANGA stands for Mapping Nearby Galaxies at Apache Point Observatory. It's a second-order acronym. This is called an acronym with another acronym. So the A stands for Apache Point Observatory. And everything that you want to know about the galaxy and is listed here, you can learn from that. And many people, there are now, I don't know, 500 publications with MANGA data have been looking at all of those things. How is MANGA done? Well, it's done. MANGA's done 10,000 galaxies. It's a sample of galaxies that is being selected to be representative of the nearby universe. And we know the statistics very well, so we can make it a complete sample and do the statistics. So what you have is that you pack fiber optics all together in something called a hexa bundle, and then you can see the size of this thing is inside a ferrule. It's got a little button there so that you know which side is up, which side is down. And then in different locations of the galaxy, you can get different spectra. Manga started back in 2017, I think, and it finished about a year and a bit ago. Manga has got 17 of these integral field units, so that you can do 17 at a time with different sizes, because galaxies on the sky, some of them will be larger than others, so it would be a waste to put this large bundle on a small galaxy. So there's 17 of those plus calibration fibers, just for the aficionados, and then all the fibers get aligned onto the slit in a very compact and very efficient way, and you get a spectrum of every location of a galaxy in each one of those bundles at the same time. Here's Anne-Marie Weidmann's plugging them by hand. Again, steel plates, you drill a hole where your galaxy is, and you put your fiber bundle there. Light goes to the spectrograph, and you get a spectrum in every location. Every observation requires a new metal plate with holes. Those have been all distributed to schools as part of, you know, engagement outreach activities. You could have all of those. I think we don't have any left, but all of those existed. So, you know, for each field, you have to produce one of these metal plates. They get bent a little bit to get the focal plane marked, and that's how you observe. And that was the commissioning plate. No, it's longer than that time. Flies 2014, in which we did the first set of galaxies, and we finished about 2 years ago. Now it's 2023. Again, time flies. If you're as old as me, remember that you do not perceive time as t, you perceive t as delta t over t. It's logarithmic. So if you're old, a year is very short. And I tell you that happens. And then we got the data for the galaxies. It's finished. And this was the first thing that we looked at. This galaxy, again, you've got the kinematic map. This side goes away, so this side goes to you. We got the H alpha, which, of course, I'm not going to tell anybody here at UCM what you get from H alpha. You get the star formation rate. Jaime started the objective survey. Jesus exploited it. We published that paper that started in industry. Now, what I've been doing is concentrated mostly on stars. And what you want to get from this information, from this data, this correction, as much information as you can. So if you got a spectrum of the location of the galaxy, and that is one of those spectrum, that is the one at the top, just comes from one location on the galaxy. Remember, you've got one for each location of the galaxy. You can do a little bit of science, a little bit of craftsmanship, a little bit of alchemy, extract the contribution of stars from different ages to the light. So here, blue means is the contribution of young stars. The orange, the yellow is more contribution of 1 billion year-old stars, and the red one is older stars. So for each location of the galaxy, you can do archaeology. You can measure, as a function of time, how many stars you formed, because you look at the contribution from stars from different ages. So you know, as a function in any location of the galaxy, how many stars were formed at any given time. You can also get the chemical composition. Of course, star formation, a little bit more of galaxy evolution. Star formation is linked with chemical evolution, because when you form stars that die pollute the interstellar medium with heavy elements, and the next generation produces stars that have more heavy elements. With that, you get working extensively on extracting on the different locations of the galaxies the star formation history, is how many stars they formed there at a given time, and the chemical evolution linked with that star formation history. That is a technique called relation synthesis. Javier Borgas taught me all about it many years ago with Patricia. I've perfected it, so many people here know about it more than I. So with those data, 10,000 galaxies for which we got integral field spectroscopy data cubes, and using techniques that allows us to extract that information, I'm going to start telling you now about the science we've got from those. And it will be a little bit of a summary. Some of it I'll spend more time than in others. Already wasted quite a lot of time due to technical details, so try not to bore you too much. But what we're trying to do is to extract time and space information on each galaxy. That is, in each location of the galaxy, in each component of the galaxy, the bulge at the center, the disk, the spiral arms, the star formation history, which gives me the time dimension, and the spatial dimension is in which location. Chemistry, the chemical evolution, is also part of the time dimension. So that's why I'm going to see it. It says spatially over this screen. It's gone out. Spatial and temporal resolved galaxy evolution with manga. In red here, of course, are the people who do all the work, which were people like Evelyn Johnston. Now she's faculty in Chile. Martha Taylor, who moved into perhaps better paid jobs in astronomy. The same with Tom Peterkin, who did an awful lot of the actual extracting of the information, and now he's selling his services to the people who make maps. Because people make maps of the surface of the Earth. There's how to extract that information. That is a message for people doing PhDs, people doing undergraduate studies, that you may not end up having a career in astronomy, but you will learn techniques that extracting special information on a galaxy can be used to extract special information on a map of a region. Okay? And Tom Peterkin is also very good. Amelia Fraser McKelvey had little sense of saying astronomy. She's now in Australia, moving to Munich. Again, did quite a lot of work. Xuan Zhu is working with us in Nottingham. Moving to Milano, I think the weather there is better, and the food is probably better too. And those are the people, some of the people who did much of the work. Of course, the people who ran the survey, the people who got the funding, the people who built the instrument, the people who did the observations, the people who resolved the data, the manga team deserve more credit, or at least as much as we do. Okay, so all the credit to the people in red, and then people like me and Mike Merrifield. Sometimes we even do something. Right, so something that has always interested me for many years, even before integral field spectroscopy, even when we had long sleep data, which gave us spatial information, of course, my Tesina, my master's degree thesis, Javier Gorgas very kindly directed, was looking at that, at the spatial variation of the spectra on galaxies. Things have moved on a little bit since 1985, 86, 87, and now what we want to do is to understand how different components of a galaxy, like this beautiful spiral galaxy, you can see it's got a component in the center, which is the bulge. It's got a disk, and it's got spiral arms. And the idea here is I want to understand how these different components form and evolve. Okay? And that is what integral field spectroscopy allows you to do if you're clever. So let's just go back here. For many years, people have done decomposed images of galaxies into the different components, into the bulges, the disks, and the spiral arms, on images. But of course, I told you before that a data cube, an integral field spectroscopy data cube, is like several thousand images in different colors. So if I can do that with an image, I can do that with a 10,000, right? Once you know how to do them, and in this case, 2,000 of these baskets. And if you can do it with images, you can do it with data cubes. And Evelyn Johnston in Nottingham developed that technique first with long slate, but then she just took, the data cube. This is a representation of a data cube. You've got images at all the wavelengths, all those images, and she cleverly extracted the information of the different components, the bulge and the disk, and then the residuals. I don't want you to look at all the details in this slide, but it is complicated. That's the message, but if you do it and you do it well, particularly your galaxy is simple enough, like a lenticular galaxy. Why is a galaxy lenticular is interesting and simple? It's got a bulge and a disk. These spiral arms do not get in the way. They're also very interesting because probably they are the smoking gun of that green valley that tells us about galaxies that were forming stars and today don't form stars. More on that later. But with that, for lenticular galaxies and for some galaxies it works quite well, and you can see the green ticks here for all the galaxies where they work. Even spiral galaxies sometimes works quite well. If you've got a complicated merger, you cannot do it because there are more components there that you can do it. And then once you got all that information, you got a spectrum for each one of those components. Right? The same way that you would have a model for the bulge and the disk of a galaxy, then you can extract with this technique the light that comes just from the bulge, taking the contamination from the disk away, and the light that comes just from the disk, taking the contamination from the bulge away. So in this plot, and the spectrum is divided in two panels just because it's very long, and that is also important. If you want to understand galaxy populations, stellar populations in galaxies, you need a long wavelength range, and that's one of the good things that we have. It goes from 4,650 more or less all the way to 10,000 amps. And you've got the spectrum of the whole galaxy, and we know which part corresponds to the disk and which parts correspond to the bulge. That means I can extract information of the different components separately. And then just again for people like Javier or Patricia will recognize these plots. What I'm showing here is that using different spectral measurements of the intensity of some spectral lines, I can extract information about the chemical composition and the age of the stellar population, including the different mixture of chemical elements. But we can do more. This can be done just by looking at individual lines, but you can do a full fitting to extract the full star formation history of the galaxies. And you can do it as a function of radius. This is what it shows here. Anyway, back in history. Back in 2010, give or take, we were looking at how spiral galaxies transform into lenticular galaxies. Galaxies in the blue cloud transform into galaxies in the red sequence. Galaxies in the star formation sequence move into the non-star formation sequence. So we looked at them in clusters. And the bottom line is that when you got a spiral galaxy that is isolated in the field, that's where most spiral galaxies live, they form a lot of stars. They've got gas, they've got star formation. Most lenticulars appear in clusters, but clusters are built of galaxies that fall onto them. So those spirals fall into the cluster, and in a few words, when a galaxy falls into the clusters at great velocities, 600 to 1,000 kilometers per second, they encounter intracellular medium, they move very fast, and the gas is removed, and that makes them stop forming stars, and you have a spiral galaxy with that happening. When we did that work in cluster galaxies and mostly low mass galaxies, we interestingly discovered that the last episode of star formation happened at the center. So we always thought that lenticular galaxies form by suppressing star formation from the outside in. That was correct, but not the whole truth. When evening did this work, we found that some galaxies are like the one at the top, and this is a star formation. This is look back time in millions of years. This is a long time ago. This is today. The one at the top, the disk, forms stars first, and then declines star formation. The bulge forms stars later, and they decline star formation. But some others, sorry, it's projecting outside that, form most of the stars at the beginning. So the story was not complete. So the interesting thing was to say, well, what happens if now we don't do the about 20 or so galaxies that we did then, and we look at hundreds of galaxies. And then Amelia, Tracy McKelvey, did that for many more galaxies, the same kind of techniques, The first thing that we discovered, and here you look here at the top, one is telling you the bulge age, and at the bottom, this age as function of the chemical composition. There are two populations of lenticular galaxies. Okay, some have got a disk that is old and metal rich, and some have got a disk that is young and metal poor, and the same with the bulges. And unfortunately, the colors cannot be seen, but light green is massive, blue is low mass. And then this is the most complex diagram I've ever published in my life with anybody, in which we put all the lenticular galaxies in the same diagram. Look, the circles mean the bulge, the disk, again, the age here, and the metallicity here, and each 2 points correspond to the same galaxy. The bulge is linked with its own disk, so here this disk is linked with its own bulge. At the top, these are mostly massive galaxies, these are mostly low mass galaxies. So if the bulge is on the right and the disk is on the left, the bulge is older than the disk and more metal rich. Okay, so if it is higher, it's older. On this side is the other way around. Bottom line, what we discovered is that the process that we have found before, that switches of star formation in the disk first and then the bulge, only happens in low mass galaxies. In high mass galaxies, the process is different. You switch off star formation first in the bulge. So this is telling you two things. One is the power of integral field spectroscopy for many galaxies, and also having a large sample. Having, in this case, we had a couple of thousand galaxies. Okay. So that's the first interesting thing that we found. We also looked at the kinematics, okay, because in order to do all the stellar population system, history, we ignore the kinematics, but now we can separate from the whole galaxy. You've got the velocity, this side moves away from you, this side moves towards you, this side moves away from you. You can get the kinematics for the bulges and disks. You can get the stellar population as well. But one of the things that we discovered in these lenticular galaxies is that if you plot them in a diagram, again, we do not see the y-axis here on the screen. The y-axis gives me lambda, which is a measure of the angular momentum. Things at the top have got a large angular momentum. Things at the bottom do not have large angular momentum. And these lines here represent the models for rotating systems. And if you look at all the galaxies together, at the whole galaxy, it's a bit of a mess, right? Things seem to be here to the bottom and there's nothing very clear. If you separate the bulges on the disks, and of course, disk is blue rectangle and bulges are round, they perfectly separate into the galaxy, into that is telling me that that component of the galaxy, the disk, is behaving like a proper rotator. It's completely supported by rotation, more or less circular orbits, but the bulges in most of these galaxies have got random motions, therefore are in the region of low angular momentum. The velocity of the stars is much random. So that's one of the interesting things we found, just not looking only at the stellar population, but also at the kinematics. We understood the kinematics of the different components of galaxies separately. Other galaxy components, we looked at bars, and in the interest of time, I'm going to escape the part about stars, but we started looking also at the spiral galaxies. And the first question that we asked ourselves was, is the galaxy like the Milky Way? Typical, or is it very strange with this kind of information? So if you've got a large number of galaxies, then you can start doing statistics. So we selected a sample of Milky Way analogs. We started from galaxies that out of about almost 650,000 galaxies, we selected about 70,000 that got approximately the same mass as the Milky Way. We selected them to be spiral. we selected them to have a bar, because of course the Milky Way has got a bar, and we had selected them to have a small bulge, a bulge that is not more than 15 or so % of the light. And we ended up with 176 of those galaxies, some of which have been observed by Manga. If you plot them on a diagram, you already have encountered star formation rate, main sequence of star formation rate, red galaxies here. All of them are all those triangles, 176 of those, which are forming stars, of course, the Milky Way is forming. So the Milky Way is kind of low in star formation, but not unusually low. And it's not exceptional, it's just on the low side. So maybe the Milky Way will get into the green valleys soon and perhaps become redder later. I don't know. I will probably be retired by that time. We looked at many more details. We started looking even at the chemical composition of the Milky Way. And out of those galaxies that were like the Milky Way, we look at things like, for the stars of the Milky Way, and those are the red points, those are real stars in the Milky Way. There's a relation between the age of those stars and the chemical composition. There is a relation between the chemical composition in the inner regions and in the outer regions. And all of those are the little dots. But we were able to look at these galaxies, like this one, with Manga, look at what happens in the inner regions and outer regions, get their star formation history and the chemical evolution history. So this is the former stars a long time ago. In the center, in this, they continue forming stars even today. The chemical evolution, well, they started having low chemical composition and they became high. And the models are the thick dots. And we were able to find that of those galaxies, about a third had the same sort of star formation history and the same sort of chemical evolution. But there were two other types of galaxies, like the Milky Way, that behave quite differently. Some of them have pretty much no star formation anywhere anymore. Okay? So we're even more extremely low star formation. And some of them had an inner region that was exactly the same as the outer region, unlike the Milky Way, in which the inner region and the outer region behave differently. So even if in a star formation history, the Milky Way seems to be typical, in chemical evolution, there is lots of variety. We can get that by looking at all of these galaxies. Got no idea how I'm doing for time. I'm probably very late. But I want to show you a few pretty things before finishing. And I'm not going to talk about that, not because it's not interesting, but it's because I've got no time. That was all about environment. And if you want to ask me about environment, ask me later. But let's have a look at some more spiral galaxies. And I remind you of the technique. In every location of the galaxy, I extract the star formation history and the chemical evolution just by looking at the spectrum in different regions. So for any spiral galaxy, I can get an image, but then I can fit the data and study the different components. And then I can extract the region. For instance, the H alpha light tells me how many stars are being formed in any region. But I can also look at the distribution of young stars, intermediate age stars, and old stars. And just to show you that you can do it for more than one galaxy, here is another, but we've done it for thousands of those. And then for each galaxy, as a function of time, you can see here these boxes, tells you time. So this is a long time ago. This is old stars, and this is young stars. You can see how these galaxies form stars first at the center, and then the star formation moved outwards. I mean, I can look at this for hours. They are so completely hypnotic. So you've got the clock at the bottom, tells you all the stars, they're moving towards new stars, and you can see that the center stopped forming stars a long time ago, but then they formed stars later again. So the variety is enormous, and I don't want to tell you these colors mean chemical composition. I'm not going to get there. You can do that, and for instance, you can see how galaxies grow with time. Okay, we know that the size of a galaxy and the luminosity or the mass of the galaxy are related, and so you can see how the galaxies with time move from being small and less massive to being larger and more massive. And you can calculate and look at, this is how they change in size. This is just the change in size for high mass galaxies in red, intermediate in yellow, and low mass in blue. This is what they do in light. They change quite a lot, right? By factors of a few for the more massive ones. But actually, if you look in mass, they don't change as much. They change only by a factor of maybe 2 or so for the. And the more massive seem to have changed in size more than the low mass. That's interesting stuff. I cannot fail by mentioning this because, you know, we started it here and Complutense. This is the famous plot in which, as a function of look-back time or redshift, this is the early universe, this is today, you can plot the star formation history of the galaxies. We put the first point, we started it here many years ago. Then other people like Piero Madau got all the galaxies in the universe and got this plot in which galaxies started having not an enormous amount of star formation. They picked a redshift of maybe 1 or 2, and then they declined. But what we were able to do it, as a function of whether in the blue cloud or in the green valley of the red sequence, so we can get the star formation history of the universe for galaxies in different categories and different masses. The one on the top is the absolute, this is in fraction. Color mean blue cloud, green valley, and red sequence, obvious colors. Dark means more massive galaxies, light, less massive galaxies. For instance, if you look at galaxies that are in the red sequence, the more massive ones form the stars earlier. We can do the same for morphology. So we can look at the star formation rate history of the universe for galaxies with different morphologies, spirals, lenticulars, and ellipticals. So you can see that if you look at the ellipticals, they form earlier, and the more massive ones, the darker one, form earlier. Even the spirals, which had a much flatter star formation history, the more massive ones started early. And we've done that just because the manga sample is large. We know how to make it complete, and we know how to measure star formation as a function. So that brings me to the end. It's been a little bit of whistle-stop tour of what I've been telling you. Just if you don't want to listen to me, just look at that animation. This is a very interesting merger of galaxies in which we can look at how stars form different times. Look at that tail form stars that are metal-rich, not say. Isn't that beautiful? Anyway, we study galaxies because they are beautiful. Don't think that the reason is any other. I've told you about galaxies. I've told you about integral field spectroscopy, and I told you about a few things that we can learn from those. And it's been great fun. We're still doing an awful lot of stuff linked with this. This mentions probably about 10 of the papers we've written on this, but there are 30 something or 40. How many? Again, done by many other people. It is great fun. Integral field spectroscopy keeps improving. It's been used in larger telescopes. We've got larger telescopes that you can look at the galaxies, look at them how they were a long time ago, compare our history of star formation, what you observe by looking at galaxies a long time ago, and all of that is working. Of course, this department has been very involved in Megara, field spectroscopy, and is involved in other integral field spectroscopy surveys that are going to happen in Colorado. And I think I'll shut up.
No, I have no questions, but I'm gonna start first for the people asking the people that is coming remotely. So, is there any question?
I don't know whether they heard me too.
I think so, because otherwise they will have complaint. Yeah. So if you have a question, just open your mic and speak up. You have a volume here. I will open mine.
Oh, hello. I have
so
a
in
question.
The meantime, is there any? In the meantime, is there anyone here that's gonna have a question?
Hey, I have a question.
Okay. You saw the work of Tower, I think it was, showing the different angular momentum or lambda of bulges and this. And you have previously shown us that you find like 2 different types of bulges. So well, depending on what is in relation with it is. So some of them were like older, and some of them like less massive ones.
Yeah.
So do you find any difference here in this diagram for these two types of points?
You see, we haven't joined up all the dots.
Okay.
So this has not been correlated with the other one. So that's, things happen, things move on, but that's a very good question. I'm going to tell you what I guess, okay? That's a hypothesis to be tested. And I'm going to say that the ones here on the bottom left, these will be older and these ones will be younger. Because in general, I would have said that these are less massive than these ones. But we haven't joined the dots, and that's a very good question. Sometimes you start research and you don't finish it, or you do something else because it's more interesting. We only have a pair of hands or a pair of postdocs or PhD students, and you got to make do with what you got.
No, I mean, my question is about, the resolution model, I don't know if I will, but you mentioned that you can have an alpha question or vice versa, but you can also have like for example, a bar that that flows gas to the center, and from like these central disks that you see them everywhere with image data. So I guess So this is the bar study, and the thing about bars is that they're very different. So these are maps of the star formation in different galaxies. And we classify them morphologically just because we like looking at galaxies. In some cases, you got H alpha quite concentrated. That's star formation, regions of star formation on the bar and the spiral arms. In some cases, all the star formation is concentrated at the center. In some cases, look at how very beautiful the bar is delineated with additional star formation at the center. Some places are less, and some places is very, very low. So here you got a beautiful lens distribution. And we try to see, are these particular kind of galaxies have got any systematic properties that make them different? And quite frankly, nothing really jumped to the eyes. I mean, have a look at the paper. It's a fun paper. Amelia Fraser McKelvey wrote it. She writes fantastic papers. She's very good. If you get a chance to invite her, she's now in Munich, so she didn't have to fly her all the way from Perth in Australia. She's coming back in September, I think. Ask her about bars. She knows an awful lot about bars of both types, of the ones that you look at here and the ones that you go to print. But she's a fantastic baker. She makes fantastic cakes. Really, really good. Okay. Well, I have to say, always asking this. I have a question when I see the decomposition, that the special decomposition. I mean, because it's always assumed that you have a disk all the way to the center and a bulge. I mean, I don't see if that's possible from the dynamical point of view. I mean, you have a bulge like dynamically hot, imagine, no? Like right now, if you can have like a disk all the way to the center that have an exponential profile because it's rotating.
Right. Yeah. How on earth? Sorry, I'm going to complain. How on earth is this so clean? Because these guys are seeing the center of the, this is the same potential well for both of them. And that is, we did this work with Michele Capellari, who most absolutely everyone that is to know as this. And he invented these box, etc. And many of these things here. And he was always very skeptical that you could get the kinematic of the ball so clearly separated in the momentum from that of the disk, because there is only one potential well, right? So and how do these stars know that if I'm in that location? Because that's how we extract whether a star is in we get exponential disk and bolts.
But the angular moment there has into account the radius, right? So the disk you have a more, even if they are rotated at the same speed, you have larger angular momentum. So maybe that also can produce like such a change. I don't know. Maybe everyone needs that.
That's a very good point. You got the radius here, and these things are large.
So I mean, I don't know. It's like, I mean, I keep asking that question because everyone will do this composition, but I'm not sure if that actually dynamical possible. I mean,
if there is physically possible. I don't know, but I mean, it's so clean. As my word. I mean, it may be what you're saying. It's just the radius doing all the work.
at something, no? We do something.
But these things are not rotating. These things are not really rotating.
Yeah, those are not really rotating. They're right. Yeah.
So you know, you make them big. I mean, some of these bulges are large. Okay, some of these bulges have got effective radii comparable to the effective radius of the disk. But it is true that they're more centrally concentrated, and maybe this is all wrong because it cannot be. But dynamically, these stars are moving.
I have no idea. I don't know.
I mean, they've got different ages. They've got different ages, so you know they might have experienced different. Even in the same potential, they might have been scattered more, or they might have been. Yeah. So who knows?
I don't know. Maybe you could get. Yeah, maybe there is nothing that you. From the center, there is nothing that.
Okay. Let's see any other.
Well, there's another question about people because I have sorry.
I have a question.
Marisa, I will open the. Can you open the volume? Okay. I'm gonna open my.
Okay. Can I ask now?
Yeah.
Oh, thank you. Yes. Thanks very much for the talk. It was very nice. So I have a question about the first part of your talk. When you talked about lenticular galaxies, you said that massive galaxies shut down first the star formation rate in the bulge, and the opposite for low mass galaxies. So why is that?
Well.
Yes.
So I'll tell you my interpretation. My interpretation is that more massive galaxies are affected less by the environment because they've got stronger gravity. And so for the process that I mentioned before, that the galaxy that falls into a cluster, the gas is removed from the outside first, it's easier. That only happens for low mass galaxies. Higher mass galaxies, two things happen to them. One is they got more mass, so removing the gas from the outskirts is more difficult. And also, they might have done all the business, all the transformation before actually they got into the cluster. Because of course there are lenticular galaxies outside clusters as well. Let's not forget that. There are less, or there are more of them because not many galaxies live in clusters, but of course, proportionally they live more in clusters. So first of all, is the mass will prevent gas from being removed and star formation more difficult, and you need another mechanism. And the other mechanism could be something like AGN activity that may happen in massive galaxies. If we look at, what is the other one? Sorry for driving you mad with all these things, but let me just get to the one that I want to show. This one, if you look at the star formation history of these galaxies as a function of morphology, so I'm looking at the greeny things here, the more massive ones did their business earlier at quite high redshift. So maybe because clusters only are still growing, and most of these galaxies didn't get into clusters until redshift of about 0.5, the star formation cessation happened before the environment happened. And if that's the case, that must have been driven by something like AGN activity, that is a black hole at the center getting fed, producing energy that gets rid of the gas and prevents and prevents star formation. And that would work first at the center. So that is my interpretation. One, they are more robust, so more difficult to take the gas out of them when they fall in clusters, but they might have done all the business. They might have done all the transformation before. And so this links this study with the other study. Did that make sense? It was Marisa, wasn't it, Marisa?
Yes, thank you.
Did it answer your question, or do you have any further comment?
No, it answered it. Thank you.
Sorry. You can talk now. You were talking.
Yes, it is. Yeah, it answered my question. Thank you.
So, yeah.
You can go back to the most complex.
The most complex block.
Yeah.
That's
So, yeah. can comment about the binaural of the plot. This can tell us something about how this guy forms.
Why is it?
Can you repeat the question for the
Yeah.
people?
Oh, yes. Yeah. So the question is a very interesting one. Why are this plot, this is observational, there is no interpretation or not much, both the bulges and disks have got a very bimodal distribution. Why is it bimodal? Why are so clearly separated? Why is not more of a continuous distribution? That is a fantastic question. I don't know how to answer it. It may be linked with why, it may be simply related to why the Green Valley is so depopulated, but I don't know why that shows here so clearly. And it's an excellent question. And if we understood, we knew the answer to that question, I think we would have understood quite a few things. Any ideas, just send them to me on a postcard. Young people, a postcard was a piece of paper, cardboard with a photograph. You put a stamp on the back and you post it, or a WhatsApp, if that's easy.
If I can follow up on
Yeah.
Also, you said that these are separated in more massive galaxies and less massive galaxies.
Yeah, and that is shown in here. There was a mass bar.
And what about if you look at the mass of how that correlates with the mass of the component and mainly bulge over this area?
Right. They're always, we looked at the bulge to total ratio, and there was not a strong correlation. So massive galaxies were massive everywhere. Okay. And if I tell you the truth, in this plot, I don't know, I can't remember whether this mass corresponded to the galaxy or it corresponded to the component.
Okay. It is the mass, yeah, but it's good. Yeah, it's here.
Oh, yes, you can see that. Yeah, I'm sorry. Yeah, oh, I'm sorry. You can see that, yes, yes. But if, sorry, yes, I can't remember because we looked at both things. That's a very good point. What it has to do with the bulge to total ratio. It is true that statistically more massive galaxies tend to have a larger bulge to total ratio, but the correlation with mass of the galaxy was stronger than with bulge to total ratio. And so, but it's a very good question again. It's just, does the size of the bulge matter here? And it didn't.
I think it's probably the component because you see you don't get any galaxy, I mean any mass above 10 to the 5 or so. So probably, I don't know where to start, but probably you have
we
this
looked at both ways, and it showed pretty much the same because, you know, within the scatter that you can imagine, because there, you know, you've got all sorts of colors everywhere. Here there's some green ones, some blue ones. Large galaxies, massive galaxies tend to have massive everything. Because the bulge to total ratio doesn't change that much, can change by factors of 2 or so, maybe 3, but the mass changes by several orders of magnitude. Therefore, mass wins.
And that's the thing because we are seeing similar things with more degree, like the compactness of the bulge. So like mass and size matter. So how much mass can you put inside given space? That could be interesting.
Absolutely, because you're talking about compactness of the bulge itself.
Yeah, of the bulge.
So a little bit linked whether there are a more classical bulge or more of a pseudo bulge. I think that not to bore the audience that are not interested, come and talk to me later. So I would like to hear this. Thanks.
Okay. More questions? Last opportunity for those of you who are at home to ask their question. I don't know, Brian, did you have the chat? You can write in the chat and then we open the meeting. Okay. Okay, then let's gonna thank Alfonso again. Thank you. Thank you for the seminar system this year. So that again is
So I'm the clothing eye. I'm the fat lady singing. Okay, thank you. Thanks a lot. Siento que